Welcome to the Explainer. Today, we're going to dive into a really fascinating corner of AI, a concept that teaches machines to understand the world just by learning how to make the perfect copy. All right, let's kick things off with a puzzle that's at the heart of so much modern AI. How in the world do you teach a machine to find patterns when you don't have any answers to give it? No labeled examples, no cheat sheet. This is the challenge of unsupervised learning. And the answer? Well, it's actually kind of beautiful in its simplicity. Instead of giving the machine the answers, you give it one simple job. Take this thing and make a perfect copy of it. The input becomes its own target. So this whole idea is the foundation for what we call an autoencoder. You can think of it like a self-taught artist, an AI that learns about the world not from a teacher, but just by trying to master the art of reproduction. So to make this real, let's imagine a master forger. Their only job is to create an absolutely perfect copy of a masterpiece. You give them a picture of a cat, their one and only goal is to create that exact same picture of a cat. That's it. Sounds simple, right? But the implications, they're huge. Okay, so how does this forger or autoencoder actually pull this off? What's going on inside that black box? Let's pop the hood and take a look. Well, the whole process is like a two-person job. First, you've got an encoder. Its job is to stare at the original masterpiece and analyze it. Then it has to write down a super compressed secret note about it. After that, a decoder gets only that note and has to rebuild the entire thing from scratch. And finally, you compare the new copy to the original to see how well it did. And here you can see that whole process in action. The input comes in on the left, it gets squished down by the encoder into this tiny, compressed form, and then the decoder has to try and blow it back up into the original. Now, that little part in the middle, that's where all the magic happens. That compressed middle layer, that's called the bottleneck. This is our forger's secret note. By forcing all the information from the original image through this one tiny little space, the network has to learn what's actually important. It can't just memorize every pixel. No way. It has to understand the idea of cat ears or the shape of a whisker. It has to learn the essence. So, how do we know if the copy's any good? That's where something called reconstruction loss comes in. Just think of it like a super picky digital art critic. It measures every single tiny difference between the copy and the original. The entire goal of training the AI is to get that difference, that loss, as close to zero as humanly or artificially possible. Okay, but here's where it gets really interesting. Not all of these forgers are the same. Over time, different types have developed their own very specific, very cool skills. First up, you've got your classic, the undercomplete autoencoder. This is our straightforward forager. Its main purpose in life is just to compress data efficiently by shoving it through that narrow bottleneck. And this is amazing for something called dimensionality reduction, which is just a fancy way of saying it simplifies really complex data down to its most critical parts. But what if we throw a curveball at our forger? What if we give it a damaged, grainy photo of the masterpiece and ask it to restore it? Well, that's the exact job of a denoising autoencoder. It's specifically trained to take messy, corrupted data as its input. And here's the absolute genius of it. The input is noisy, but the target, the thing it's trying to match, is the original clean image. By doing this thousands of times, it learns to see past the static, to recognize the signal in the noise. It literally becomes a master art restorer. Now, this shows a totally different strategy. This is a sparse autoencoder. Imagine giving our forger a massive notebook, but telling them they can only write down a few very specific notes. Even though they have tons of space, they're forced to be sparse. This makes the network learn really distinct, separate features, like one little note just for eye shape and another just for nose position. And finally, we get to the true master artist of the family, the variational autoencoder, or VAE. This one is so good, it doesn't just copy the masterpiece. It learns the style of the master. It learns the deep-down rules of their art. So how on earth does it do that? Well, instead of that bottleneck being a single fixed secret note for an image, it learns a whole range of possibilities. It learns a probability distribution. This creates a smooth, continuous map of features, a latent space. You can think of it like a map where all the cat-like features are in one country and all the dog-like features are in another. By picking a new spot on this map, it can generate a completely original image that's never existed before. It moves from just copying to actually creating. So, this all sounds really cool, right?
But what can these different techniques actually do in the real world? Well, the applications are seriously powerful.
I mean, this ability to just get the essential structure of data is used everywhere. Denoising autoencoders are cleaning up old, grainy photos and audio recordings. Others are incredible at anomaly detection, right? If you train a network on tons of legitimate financial transactions, it gets really, really good at spotting a forgery, a fraudulent transaction that just doesn't fit the normal pattern. So let's just boil it down. The key point is that by learning this simple trick of copying, these networks become masters at three absolutely critical things: compressing data, extracting meaningful features, and in the case of VAEs, even generating brand new stuff from scratch.
Okay, let's pull back for a second and just think about what this all means for the bigger world of machine learning.
So, what are the big takeaways you should remember? First, autoencoders are so powerful because they learn from unlabeled data. You don't need a teacher. They work by this process of compress and reconstruct. That bottleneck is the absolute key, forcing them to learn what's truly essential. And as we've seen, the different flavors of autoencoders can do all sorts of things, from cleaning up noise to dreaming up new data. And that leaves us with this really mind-bending final thought. If the simple act of copying something perfectly is enough to teach a machine the deep, underlying structure of our world, the essence of a song or a face or a landscape, what's going to happen when these self-taught artists really start to create?